A buck regulator is a DC-DC converter which converts a higher voltage potential to a lower voltage potential. It uses a switching element to ensure steady DC output of required voltage. I am Reshma, and today we will discuss the operation of a buck regulator. In this video today, we will learn how to calculate the value of inductor, average and peak currents of the inductor, losses in the inductor, conduction loss of the switch in both MOSFET and IGBT, switching loss of switch in both MOSFET and IGBT, diode conduction loss, and synchronous switch losses. Let us look at the inductor conduction loss. For an inductor, the conduction loss is due to the DC resistance present in them. Let us call this as R inductor DC. In a resistor, the power loss is given as I square R. The power loss is directly proportional to the square of the current flowing in it. The figure shows inductor current waveform. Here, we can safely say that power loss due to the DC resistance in the inductor is directly proportional to the square of the inductor current. That means I1 and I2 is squared as shown here. Thus, we can say that power loss of the inductor is P inductor DC of T, that is equal to I square L of T into R inductor DC. Now, the average power is given as the integration of power over one cycle. Let us substitute the value of power loss equation from our previous slide. Since the DC resistance is constant, we can take it out and now we have to integrate only the current. From our previous video, we have seen that inductor RMS current is equal to this. We can substitute this in above equation to get average inductor power, that is the product of square of inductor RMS current and the DC resistance. From our previous videos, we saw that inductor RMS current is the square root of I1 square plus I2 square plus I1 I2 divided by 3. RMS current is also equal to the square root of average inductor current and square of ripple current divided by 12. With these two equations, we can write average inductor power loss. This is equal to R inductor DC into I1 square plus I2 square plus I1 I2 divided by 3. This is also equal to R inductor DC into square of average inductor current and square of ripple current divided by 12. Let us now look at the switch conduction loss. Let us assume that we have used a MOSFET for a switch in the buck regulator. For this MOSFET, conduction loss is mainly due to RDS on resistance. In a resistor, power loss is given as I square R. Power loss is directly proportional to the square of the current flowing in it. As this is a switch, the current here is the switch current. Here we can see that power loss in the switch is directly proportional to the square of the switch current. Thus, we can say that conduction power loss of the switch is equal to switch current square into RDS on at any given instant of time. Now, average conduction power loss is given as the integration of power over one cycle. Let us substitute the value of power loss equation from our previous slide. Since RDS on is constant, we can take it out and have to integrate only the current. From our previous video, we saw that switch RMS current is equal to this. We can substitute this in the above equation. Now, we get average switch conduction power loss as a product of square of switch RMS current and its RDS on resistance. From our previous videos, we saw that inductor RMS current is square root of D into I1 square plus I2 square plus I1 I2 divided by 3. RMS current is also equal to the square root of D into average inductor current and square of ripple current divided by 12. With these two equations, we can write average switch conduction power loss. This is equal to RDS on into D into I1 square plus I2 square plus I1 I2 divided by 3. This is also equal to RDS on into D into average inductor current square plus ripple current square divided by 12. Let us assume that we have used IGBT as a switch in the buck regulator. For this IGBT, conduction loss is mainly due to VCE SAT. The conduction power loss of an IGBT is the product of its VCE SAT voltage and the current flowing through it. As this is a switch, current here is the switch current. Hence, conduction power loss of IGBT is given as I switch into VCE SAT. Here we can see that loss in the switch is directly proportional to the switch current. The average conduction power loss is given as the integration of power over one cycle. Let us substitute the value of power loss equation from our previous slide. Since VCE SAT is constant, we can take it out and now we have to integrate only the current. From our previous video, we have seen that switch average current is equal to this. We can substitute this in the above equation to get average switch conduction power loss, which is equal to VCE SAT into I switch average current. We have seen from our earlier videos that switch average current is given as D into I1 plus I2 divided by 2. Average switch current is also equal to D into I average inductor current. Hence, on substituting this in the conduction power loss equation, we get P average switch is equal to VCE SAT into D into I1 plus I2 divided by 2. This is also equal to VCE SAT into D into inductor average current. Let us now look at the switching loss of a switch. When the gate voltage is applied, the switch is turned on. As the switch is on, the voltage across the switch is 0 volt. The current flowing in it is the inductor current. Now the switch is said to be turned on. However, the switch takes some time to be fully on. This is the fall time of the switch. We have approximated this voltage fall as linear function. When the switch is turned on, the current gradually rises. It reaches the inductor current I1. Let us approximate this current as a linear function. During this time, the switch voltage falls from Vin to 0 volt. This time duration is in terms of nanoseconds. However, it varies from MOSFET to MOSFET. This rise and fall time can be obtained from the datasheet of the MOSFET used in buck regulator construction. Let us first look at the switch current. We know the equation of a straight line. Let us consider the time period from 0 to Tf. For this time, the coordinates of the switch are y2 x2 is equal to I1 Tf and y1 x1 is equal to 0 and 0. This means y1 is equal to 0, y2 is equal to I1, x1 is equal to 0, x2 is equal to Tf, x is equal to T, y is equal to I switch of T. If we substitute these values in a straight line equation, we get the falling current of the switch as I1 into T by Tf. Let us now look at the switch voltage. For the time period 0 to Tf, the coordinates of the switch voltage are y2 x2 is equal to 0 Tf, y1 x1 is equal to Vn 0. This means y1 is equal to Vn, y2 is equal to 0, x1 is equal to 0, x2 is equal to Tf, x is equal to T, y is equal to switch voltage. Let us now substitute this value in the straight line equation. We get the falling voltage of a switch as minus Vn by Tf into T. Knowing the voltage and current, let us now look at the power loss. Power loss is nothing but the product of voltage and current. Substituting the value of voltage and current, we get power loss of the switch during fault time is equal to minus Vn into I1 divided by Tf square into T square. Now, the average power loss is given as the integration of power loss over one cycle. Let us substitute the value of power loss equation. Thus, we can take the constants out, and now we have to only integrate T square over time. The integration limits are from 0 to Tf. Let us substitute the value of T after integration. Here, Tf and Tf gets cancelled. The negative sign indicates the power that is lost in the device. If we take only the magnitude part, then we get the power loss as Vn into I1 into Tf divided by 3T. We have seen earlier that when gate voltage is 0, the voltage across the switch is the input voltage. At this time, the switch is set to be turned off. As the switch is turned off, the current flowing in it is equal to 0 amps. Now the switch is set to be completely turned off. However, the switch takes some time to be fully off. This time is the rise time of the switch. We have approximated this voltage rise across the switch as a linear function. When the switch is turned off, the current gradually falls. The inductor current falls from I2 to 0. Let us approximate this current as a linear function. During this time, the switch voltage rises from 0 volt to Vin. This time duration is in terms of nanoseconds. However, it varies from MOSFET to MOSFET. This rise and fall time can be obtained from the data sheet of the MOSFET used in buck regulator construction. If we follow similar steps as in calculating the power loss during turn on, we can calculate the power loss during turn off. This is equal to Vn into I2 into Tr divided by 3T. Thus, total power loss during switching is the power loss during the rise time and power loss during the fall time. On substituting these values, we get this equation. On simplifying, the total power loss in the switch is given as Vn into I1Tf plus I2Tr divided by 3T. Let us now look at diode conduction loss. We know that when the diode is conducting, the current flowing in the diode is the inductor falling current. The voltage drop during this time is the forward voltage drop. Let us call this as Vf. We know that power is the product of voltage and current. Here, current is the diode current and voltage is the forward drop of the voltage. The average power loss is the integration of power over one cycle. Let us substitute the value of power loss equation. Thus, we can take the constants out and we have to only integrate the current. From our previous videos, we have seen that the diode average current is equal to this. Thus, average diode power loss is the product of diode average current and forward drop of the diode. We have seen from our earlier videos that diode average current is equal to 1 minus D into I1 plus I2 divided by 2. average diode current is also equal to 1 minus t into inductor average current. Hence, on substituting this value in the power loss equation, we can write power loss in the diode is given as Vf into 1 minus t into I1 plus I2 divided by 2. This is also equal to Vf into 1 minus t into inductor average current. In certain designs, we use switch in place of a diode. This is mainly done to reduce the power losses. This switch is called as the synchronous switch. From our earlier discussions, we saw that when we use a MOSFET, the conduction losses are directly proportional to the square of its current and its RDS on. Thus, conduction power loss is given as synchronous switch current square into RDS on. Now, average conduction power loss is given as the integration of power over one cycle. Let us substitute the value of power loss equation. Since the on resistance is constant, we have to integrate only the current. From our previous video, we have seen that square of diode RMS current is equal to this. Thus, average synchronous switch conduction power loss is the product of square of RMS current and its RDS on resistance. We have seen from our earlier videos that diode RMS current is the square root of 1 minus t into I1 square plus I2 square plus I1 I2 divided by 3. RMS diode current is also equal to the square root of 1 minus t into inductor average current square plus ripple current square divided by 12. Hence, on substituting this in the value of conduction power loss equation, we get RDS on into 1 minus t into I1 square plus I2 square plus I1 I2 divided by 3. This is also equal to RDS on into 1 minus t into average inductor current square plus ripple current square divided by 12. This is the summary of different losses in a buck regulator. It should be noted that actual losses may vary from these equations and it needs to be measured practically using suitable equipment. In this video, we saw losses in the components used in a buck regulator. We will learn more in our subsequent videos. Until then, let's keep exploring and learning. Thank you.